We good? All right, cool. All right, guys, we're going to get started. So thanks, everybody, for coming. I appreciate it very much. My name's Pitt Fagan. I'm one of the organizers of the meetup. The other organizer is Matthew Rathbone here. Before we get started, the current talk, of course, is machine learning and big data at Spotify. So thanks, everybody, again for coming. I'd like to thank Cloudera, or we would like to thank Cloudera, who is our meetup sponsor for the food and drinks. So no one from Cloudera is here, so we don't need to applaud, I guess. But anyway, thank you, Cloudera, for being our sponsor. We always have one meetup a month. Meetup's always on the last Tuesday of the month, with the exception of November, just because of Thanksgiving, and we don't have one in December. So the next one is late February. It's a deep dive into Cassandra, and I'll sort of announce this through meetup.com after this, but so it's deep dive into Cassandra. The March one is how AmFam is sort of utilizing Hadoop at their organization, and the April meetup is the data science behind Sudoku. So that should be really exciting. If anybody has any idea for any presentations, of course, we're always looking for presenters. Please come see me or please come see Matthew, and that would be wonderful. Before I turn it over to Andy, Nathan here would like to kind of announce his new computer vision meetup, so I'll let Nathan do that.
Not much to announce other than I've started a computer vision meetup group in Madison. So if any of you are interested in joining, we're going to be focusing on computer vision, extracting features from images, data video processing, along with visualization of data. So I figured this would be a great place to announce that meetup. Looking forward to seeing some of you there.
Cool. All right, thanks, man. Awesome. So I'll turn it over to Andy. Thank you again. Andy's a repeat. Greg?
Can I announce my Excel group?
Sure.
Okay. Like I said, we're doing Excel on Thursday nights. We're doing it this Thursday, and I think we're going to be strong through this whole year. So if any of you want to slum it with us in the Excel world.
Cool. All right. So Andy Sloane is a repeat presenter here. He kind of presented late last year on Luigi, which is a batch processing framework that Spotify open source. And so now he's talking about his real passion, which is machine learning. So I'll turn it over to Andy. Thanks, Andy.
Thank you, Pitt. Alrighty. Okay. Thanks for coming, everybody. I'm Andy Sloane. I work for Spotify. About a month from today, it'll be 2 years now. And yeah, I work in it's called the What to Play tribe. This is my stupid logo on our hoodie. We do recommendations, recommender systems, and things like that. So like the radio thing is kind of under that umbrella. So basically, anytime you want to figure out what you actually want to play, we kind of take what you've been doing and give you more of that. So I guess I'll jump right into it. So Spotify right now has 60 million monthly active users. We're growing super fast, especially in the recent few months. We have 50 million tracks in our catalog. So these are uploaded. We get about 20,000 a day uploaded by various labels and everything. But it turns out that, it's totally obvious to record people that in the US you can't play the UK album because those are different releases. So the different labels from the different regions and stuff will upload exactly the same album. It's the same audio, but it's been encoded slightly differently. It's like 3 seconds longer. So we match those things up so that, if you're looking at a playlist that somebody in some other country made, you can still play the tracks. We'll match them to a local album. So it turns out, and the other thing is that there's so much random stuff in there, like train sounds and cell phone ringtones with fart noises, and there's tons of sound effects albums. So in terms of actual music that's been played more than 500 times, there's about 4 million unique songs that we kind of include in our recommendable catalog, let's call it. So, wow, it's dark. So what is our data for this sort of system? Every application in Spotify, and by that I mean every backend service, logs what happened in the client or whatever. And these are delivered via Apache Kafka. So what happens is all logs are kind of reliably delivered onto HDFS. Every hour they're rolled over and so forth. So we have everything on HDFS that we need. Some other stats, the most popular track right now, Wake Me Up by Avicii, 330 million plays And if you look at the different people who've played it, there's at least 6 million different people who've played that same track. So in terms of the actual application logs, what we're mostly interested in is called end song, which is an event that's logged every time somebody finishes playing a song. And that rolls up to about 500 gigabytes a day of logs. But when we, so that's just like one event per user per play. So if we roll that up and say, okay, well, this user's played this track 20 times in the last year, that's a lot less data. So it only turns out to be about 60 gigabytes of data that we're training on for this example. So, it's not maybe big data. You could theoretically do all this on one machine if you wanted to. And in fact, these days it might be faster to do it, but we wrote this all 4 years ago or something. And the other thing is with our growth, we can handle any number of users right now. Spotify's Hadoop cluster, I think, is the biggest in Europe. We have a London data center with 900 nodes right now. Just because we're doing machine learning, the amount of RAM available is kind of important. So there's 34 terabytes of RAM total. We typically run about 16,000 concurrent tasks, which is mappers, reducers, or like Spark executors, or whatever. We're using, Hadoop 2 has got yarn, so you can do other things besides map reduce. But we have 2 gigabytes of RAM per mapper reducer slot. So anyways, what do we need machine learning for at Spotify? The main things are recommendations, related artists, and radio. Related artists is, if you're looking at an artist page, you can just see what other people play that same artist. I'll show you that later. So, recommendations. The recommendations show up on what's called the Discover page on Spotify, which is in the background here. It kind of shows you just a bunch of album covers of stuff that you might like based on stuff that you've listened to before. We build it every day it's based on the number of monthly active users. It's not the total number of users, but it's the users who are active. We rebuild it every day. 60 million active users, 4 million tracks. And it's kind of a pipeline like this. You kind of have your Spotify users. It logs what they're doing onto HDFS. We do stuff using Luigi pipelines. We do stuff which I'll talk about. That's dumped into Cassandra. Bartender is a service that mixes up the recommendations and just serves them randomly to you, and then that shows up in the client again. So, how do we actually do this? What do we even do? Has everybody heard of collaborative filtering? Does anybody know why it's called that? Because I don't. So you have two different users. He likes PQ and RNS. He likes QRS and T. Well, they both like QRNS. So he should check out P. You should check out T. I hope that made sense. But how does that actually work? So let's envision that there's kind of a matrix of number of times a user has played a song. So here's me. Should I use the laser pointer here? Would that be easier for everybody to see?
Probably.
Wrong button. Other button. Okay.
You should turn this off.
Okay. It's just not bright enough to show up on the screen. Oh, it's got enough. Okay. There we go. It kind of, is that even visible?
It's fading.
Yeah. All right, well, on the video, it's down here anyway. So anyways, this column is like everything I've played. That's me, Andy. And like this row is the song Tub Thumping. And I've played it 13 times. Somebody else has played it 9 times. Somebody else has played it 4 times, etc. So that's what I was talking about when I was saying we kind of roll up user item play count, so that's only 60 gigabytes of data when you have this big sparse matrix. But we need to find out either how the rows are similar or how the columns are similar. So we can kind of envision, well, maybe these two are similar, like these two people are kind of similar because this product is pretty big. But you can envision people who are more similar than that. Same with items, items that are, the counts are kind of, wherever the counts kind of line up, those are kind of similar things. But how do we how do we formalize that? What does it mean to do that? We want to come up with some distance between either every pair of rows or columns. So that would be, for 60 million users, we could compute distance between every single user. That's a lot. That's a lot of operations. So we need something smarter. By the way, this probably isn't legible, but Twitter has a blog post that's pretty interesting. If you guys want to check out my slides later, you'll be able to see the link. But they have an interesting approximation where you can actually do this like all pair similarity approximately in a different way than what we're going to do later. So what we want to do instead is take up that virtual matrix and approximate it somehow, and approximate it in a way that's linear in the number of users and items. Rather than the linear in the product of those two things. So here we have a matrix. It could be, it's something related to this user and this item is here. And so if we had a two-dimensional vector that we wanted to approximate this giant matrix with, this would be, let's see, this would be the second row. So this would be this item, just a two-dimensional vector, and this column would be the two-dimensional vector for this user. So when you multiply these two, hopefully you get something close to that. So we have to find a way to find those two things. But those are a lot smaller than this. This would be, this would be 60 million times 4 million. This is 4 million times 2, and this is 60 million times 2. So a lot smaller. So why do we even want to do that? Well, if you have vectors, like I said, it was smaller, but you have this nice compact representation of what it means to be this song, like, and what your musical taste is, for instance. So you kind of call this, they're called latent factors. So if you just take 2 of these dimensions rather than all 6 of them or 7 of them, they kind of form this n-dimensional space. In a two-dimensional case, you can actually just plot that vector. It looks like that. So yeah, we typically use between 40 and 200. In fact, most of the time we use 40 for the algorithms that we use. So yeah, it's easy. And if just a quick refresher on what dot products are, it's like you take 2 vectors, you multiply each element across this way, then you add those all up, and that's your dot product. So in this case, it would be a slightly bad recommendation. And then to illustrate the exact same thing graphically, the dot product, these dotted lines are where the dot product is the same. So as you go this way, it's better. So track X is slightly worse than track Y, just because the magnitude of track Y is bigger and it gets further along that direction. Is that clear? So, if you train one of these models in 2 dimensions, 2 dimensions is not quite enough to express what's going on. So it looks a little muddy, but you can kind of see what's happening here. Metal is up here, classical's down here, very far away from metal, and you get kind of a mix of everything else. So the main workhorse algorithm we use for this is called implicit matrix factorization. It's by 3 authors. Yehuda Karen, the middle author, is one of the guys who won the Netflix Prize Challenge. So what we want to do, we want to predict, rather than predict the number of times somebody's played something, we just want to predict whether they played it or not. And, if somebody's played something once, it's not that great of a signal, but we'll deal with that later. So it's kind of like what I was showing before. You've got this P matrix, which is just whether a user has played something or not. And you're approximating it with X, which is the user vectors, and Y, which is the item vectors. So if you take X times Y transpose, which is the outer product of these big, tall matrices, you get something that's close to P, hopefully. The reason it's called implicit matrix factorization is because we don't know, we don't have people saying, do you like this? It's 5 stars, it's 1 star. We just have you playing stuff. We don't ask you. So the Netflix Prize Challenge was like, you were given 5 stars, 3 stars ratings, and you had to predict what star rating you'd get. But this, you just need to know what they're likely to play or not. And we're actually trying to predict whether somebody's going to play that track or not. And that there's a slight problem with that because music, very popular music is likely to be played by everybody, even if they not really into that. So we have to kind of take care of that later. The model doesn't explicitly model that. So we want to make, so x sub u, the user's vector, y sub I, the item vector. We want to make the dot product of those two things close to 1 for things that they've played and close to 0 for everything else. So x sub u, y sub I, p sub ui, these are exactly the same. These are these matrices here, just kind of broken up into columns or elements. C sub ui, there's this other thing where we call confidence. And it's a completely ad hoc thing that you add to the algorithm to kind of take care of what it really means to have played something 50 times versus 1 time versus 0 times. So we're actually we used to use 1 plus alpha times the number of plays, where alpha was something like 200. And the reason that you need something kind of big is because you've played so many fewer tracks than you haven't played. So you need to kind of balance those two things with this fudge factor. And now we're using something like 1 plus log of 1 plus items or something like that. They recommend a bunch of different things in the paper. And then we need a regularization penalty, which I'll explain. So there's our objective. By the way, I've heard that for every equation you put on the screen, you lose half your audience. And there's like 127 people signed up. So I think after the 7th slide, I'll be here by myself. So what is this equation? It actually is not that complicated. So p sub ui is the thing we're trying to predict. It's 0, 1. XU transpose y sub I is the same thing as a dot product, just because these are column vectors. So if you put them like this, that's a dot product. So we want to minimize the square difference between each play or non-play and each vector dot product. And then we multiply that by the confidence, because if we've only seen it once, maybe it's not that important that we fit the equation or fit the cost function to that. On top of that, we have this, it's called the regularization penalty or the L2 penalty, where we basically take the magnitude, the squared magnitude of each vector, which is the length of the vector squared. And the reason we add that is because there's nothing else in the equation preventing like the user vectors to blow up to like magnitude 100, and you can then fit the item vectors to magnitude like 1/100th. So you have these huge vectors and these tiny vectors, and it still fits the objective exactly the same, but it kind of overfits and it kind of goes nuts. So this kind of penalizes vectors from getting too big. So they should have magnitudes close to 1 because our objective is close to 1. So if you wave the magic calculus wand and do a bunch of algebra, you get this horrible looking equation. But it turns out that rather than doing, like in a lot of these algorithms, you have to do gradient descent, you need learning rates and all kinds of things. This is a completely closed form solution to the problem, except that you have to iterate. Given all the items, so if you have all the item vectors or some random item vectors, you can solve all the user vectors in one step. And then if you do that, then you can flip it around and solve all the item vectors given the user vectors in one step. So this is pretty horrible looking, but it's not that complicated. What you have to do, this y transpose y term, it's a matrix that's the size of the dimensions that you've chose as a square. And all you do is you add up each item. You take each item's vector, you take the outer product of it with itself, which is the same kind of thing you do when you're getting a covariance matrix or something like that. So instead of doing a dot product, you do an outer product, which makes a square matrix. So you add up that for all items. Here, you do the same thing. This C sub superscript u minus I, that is your confidence term minus minus the 1 fudge factor. So if you haven't played an item, that's 0. If you have, it's non-zero. So only the items you've played get this term where you do the same thing. You take the outer product of the vector, add them all up. This is just the kind of weighted sum of all the item vectors that you've played. So P sub u is whether you played it or not. So if that's 0, there's nothing here. C sub u is that confidence fudge factor. Y is the item vector. So all you do is you add up all the item vectors you've played times your confidence factor. So yeah, each iteration only depends on the input. Only depends on user item count plays. It doesn't depend on anything that it doesn't depend on how many items that you haven't played. And when you go through it, you need to do a matrix inverse. But this matrix here is, in our case, 40 by 40, and then that's a 40-dimensional vectors. It's like NumPy lineage solve. So it's really easy to implement this. So yeah, there's no learning race, but you have these parameters. F is the number of dimensions that you choose. Lambda is your regularization that just keeps things from blowing up. You don't really need to play with that too much. Alpha is your confidence fudge factor that kind of depends on how many items you have typically played versus not played. So yeah, you pretty much have to add stuff up, solve a matrix, and repeat for every user or every item. We typically use 40 dimensions, as I said. And then when we implement this in Python, we use NumPy. We implement it in Scala as well, using Breeze.
What is Breeze?
Breeze is just a linear algebra package. I don't remember what it's based on. But we've also used like JAMA in Java and like Open JBlast or something like that. We pretty much just picked anything that could solve matrices. Actually, I'm using what's called EJML in Java now, which is the enhanced Java matrix library or something. I don't know. It's Google made, but it's not important really. So here's the thing: any user can play any item. So when you're looking through this stream of user item counts, you might need to add any user vector to any item vector. So if we put all the user vectors in memory all at the same time, it's going to take something like 10 gigs of RAM for what we're doing. So our mapper slots, as I mentioned before, they're 2 gigs. I mean, we could take a bunch of mapper slots, but our machines don't have that much RAM, so it really wouldn't work to do it all in one mapper or whatever. Even on a single machine, we could do it. It would just be kind of serialized and slow. So instead, we kind of break things up. This might be a little small to see. But what we do is we kind of choose a dimension here to split things up. So we have these vectors L and K. And so we split the item vectors up L ways. And the percent, that means U modulo K is 1, I modulo L is 1. So kind of the first vector goes here, second, third, fourth, etc., and then it wraps around again and again and again. So this one gets the 0th vector, and the Lth vector, and the 2L, etc. This is 1, L plus 1, 2L plus 1, etc. So, in fact, I think I explained that a little bit better. Oops. But yeah, we break the data up this way so that each chunk only needs some subset of vectors in memory. And because of the way we do these iterations, they're alternating least squares, we're either adding up items or adding up users. And so on the first iteration, we kind of reduce this way for all users. And the second iteration, we reduce this way. It's the same code, we just kind of flip the items and users around. So on the first iteration, we add up all users based on their item vectors, and we add up all items based on their user vectors. So within a mapper, what we do is we stuff all the previous iterations vectors into the distributed cache. Now, how many people are familiar with the distributed cache in Hadoop? Not many? Hadoop it's called distributed cache, and what it means is you can stuff a bunch of data on HDFS when you set up the job. And when the job launches on your mapper or reducer or whatever, it actually clones it over to the local file system. And so it's available for loading off the local disk. So you don't have to go out to HDFS to find this stuff. So we kind of use that trick. So we map the user item count tuples and we add stuff up. Every mapper emits its own contributions to that particular user, to the reducer for that user, and the reducer produces a new vector. So here's an untested Python Luigi implementation of this idea. I don't know how many people are too familiar with Luigi, but it's basically a front end to streaming MapReduce. And so your mapper gets one input per user item count tuple. So for each user item count tuple, we compute the ad hoc confidence function, like 1 plus alpha times count, for instance. Then we add up the user vectors from the previous iteration. Now we have to be careful about how we load these user vectors, but I kind of explained how it's done. And then we take, there's 2 terms to compute per user item pair. So we just need to add up the user vector times its confidence, and then we add up this outer product times confidence minus 1, thanks to whatever algebra leads you there. So then you yield, for each item you yield, this is a little overcomplicated, but basically just those 2 terms. This term is a k-dimensional vector or f-dimensional vector, and this is a matrix, a square matrix. So in the reducer, you receive everything that the mappers have emitted for that particular user or item, in this case item, and then you just sum them up. You sum up all the term 1s and sum up all the term 2s. I kind of took a shortcut there. And then you use just solve. This whole term here is this square matrix. This is term 1 is the sum of all your item vectors, and that solves it. That gives you a new item vector. So we implemented this in Java MapReduce. The main reason we actually went down to just raw Java MapReduce is because we need to implement a custom partitioner to make that whole gridification stuff work. So that when when your mapper emits a particular user, you need to go to shard, whatever, user number mod k or whatever. If you don't specify a custom partitioner, then they won't go to the right shard when you try to load them up using this distributed cache hack. So in this algorithm converges pretty fast in terms of iterations. Each iteration for all our users takes about 20 minutes. With job scheduling time, that adds up to like 7 or 8 hours. So we compute this whole thing from scratch every week. But the nice thing is, because of the way you can solve user vectors given item vectors, and you're not retraining anything, there's no learning rates, you're just re-adding all the items that somebody's listened to in the intervening period, and then just recompute their user vector. It's a pretty fast job to keep them up to date. All right, so we have vectors. We have user vectors and item vectors, but now what? So if we wanted to, for every user, find out, which of the 4 million tracks fits them best, or which top 1,000 out of the 4 million tracks is the best for them, we can't just do a brute force. We can't say, for every user, look at every item. It's just too big. So what we use instead is locality-sensitive hashing. And my boss, Eric, wrote a library called Annoy. It's open source on GitHub. And it stands for approximate nearest neighbors something something. He couldn't come up with a backronym that actually fit. But so this is kind of an illustration of the basic idea. Every little dot here is some track. And they're kind of split randomly. And every colored region is like a leaf node in this kind of random split. And actually it does it, and because you can get kind of unlucky, like this yellow one here is right next to that orange one, it actually does it several times so that you get kind of a bunch of random splits. And it actually works pretty well. So what you do is you kind of pre-build these databases, these trees, just by loading it up and feeding in all the vectors and saving them. Internally, it takes all the items, it loads them all into memory, because we only have 4 million items. That's not too bad in terms of memory. We split them all just randomly. We take a random split plane, and if it's like unlucky, then we throw it out. But if it's roughly halfway, between whatever items are left, then we recursively build a tree. Do it a bunch of times because every tree we add makes the approximation slightly better. So, given an f-dimensional, like 40-dimensional in our case, we can find the similar items in the database. And we load the index via mmap, memory mapping. So, for instance, if we did this on Hadoop, like any mappers that happen to be on the same machine would actually share that memory. And in fact, if you're using a backend service, then all workers on that machine also share the memory. It also keeps the cache nice and hot. The queries are very, very fast, and I'll show you this, but they're approximate. Yeah, we have a Python implementation. It's actually C++ with a Python interface. I wrote a Java client, but I didn't open source it. I forgot to, so I will do that. So when we generate all the items, the index, are we at a half-hour mark? Okay. Can everybody hear me okay, by the way? Yeah, okay. Alrighty, so we build all this. So our annoy index is only 1.5 gigs, or 1.2 gigs. So I actually have one of these indexes built on my laptop, and I can give a live demo of how this thing works. I need a volunteer to name a track. Any track, any song.
Shake it off.
Shake it off. All right. So, oops. Where's my mouse cursor?
Yeah, if it works.
So I need to obtain the track URI first, because I don't have a search URL. Is this the right one? Us the Duo, is that the right one?
That's the lady that took her song off of Spotify.
Oh, well, oh, wow. All right, just Taylor Swift. Okay. You got me. All right. Something else. I bet name the Beatles are probably not on here either.
Across the universe.
Uh,
Why not Fiona?
Fiona Apple, there it is. All right. All right, come on. Where's my terminal? Okay. So if I just generate the top 50 tracks for that URL, I get that. So that was how long it took to query a bunch of tracks off my laptop, which doesn't have this thing cached, and to load all the metadata. So of course, Fiona Apple Across the Universe is the most similar track because it's exactly the same track. But then here's a bunch. I mean, I could actually generate a playlist from this pretty easily. For some reason, we got a bug in our artist metadata. Sometimes they're missing. But
That's all based on plays. It's not based on similarity of the tracks, or
it's based on similarity of the tracks via the users who play them,
yeah,
using the algorithm I just outlined.
but not like based on any sort of analysis of the music. It's all based on the play counts.
Correct.
And that's you as the user, correct? Because you're logged in.
No, it's.
All.
Oh, so what I did there. See, I kind of cheated because I didn't create a user vector there. I just took the item vectors and found the closest item vectors, which I haven't really talked about yet. And in fact, what we could do is create a virtual user that it only played that one song and then had not played anything else, and that would perturb it a little bit because it would then be trying to drive everything else to zero, and then things would change a little bit. Doesn't make a huge difference though. So I don't know. Does that look reasonable? All right, it's working. So now that's oops. Oh, that's the number of recommendations to generate. I can crank that up. But so I mean, my laptop just did that in 0.12 seconds out of a library of 4 million tracks. It's a lot faster if you do it on a server that's got a live cache and everything.
Is it linear? So say you ask for 200.
Yeah. I can ask for more. In fact, I'll show you the code. So Sparky is another Spotify. We're very NIH. Sparky is an on-disk cache, similar to Tokyo Cabinet or something like that. This is the way you load an annoy index. You actually have to specify how many dimensions because we didn't save that in the file. I don't know why.
Why do they call it annoy index?
Well, annoy is the approximate nearest neighbor algorithm, and it's kind of an acronym that doesn't really make sense. So
How did you hit on 40?
40 is the number of dimensions that we trained this on.
Yeah, how did you hit on?
We just experimented with a bunch of stuff, and it gets. I don't have a diagram in here of that, but as you add more dimensions, it gets better, but it's just diminishing returns. And you've got that like 40 by 40 matrix, so as it gets, the squared size of that actually kind of increases the intermediate data that you're generating. So it's helpful to shrink it down a little bit. Yeah.
Why did you decide what dimensions, 40 dimensions to use?
Well, we tried a bunch of stuff, and 40 was sufficient to make it work pretty well without being too big.
Obviously, each one of those dimensions is different items or something like that.
No, every item is a 40-dimensional vector. and every user is a 40-dimensional vector. And those individual dimensions, I mean, you could look at them because they're all technically latent factors. So you could sort the entire universe by, like, the first element. And you kind of get something by doing that. You kind of see music separated out that way. But they don't tend to be anything you can explain as a genre.
How are the dimensions defined?
How are they defined?
How are they calculated? Like, how do you know what is dimension one? Is there a definition for dimension one?
Well, no. See, if you run this algorithm like 50 times, you're going to get 50 different answers. So, yeah, the whole space will rotate around in different ways, and so there is no way to, unless you add another penalty term in there somehow that says, okay, well, the Beatles have to be in dimension 0, and that's it, or something like that. You could probably do that. We haven't messed around with that. No, yeah, I mean, the entire space of tracks will kind of move around in the 40-dimensional space throughout the training process. But after about 20 iterations, it's pretty settled in, and it's not going to move anywhere.
So if you rerun the recommendation twice or 3 times, you get
Yeah, every time you run it, you get slightly different answers. The stuff that comes out of it is pretty much the same, but the actual vectors that you generate will be different. Because if you take all the vectors you have and just rotate them, you get exactly the same answer out of the algorithm. The fit is just as good or bad. So there's nothing really constraining the space to be in any particular direction.
So you're using the dimensions to define this set of attributes.
Yeah, I guess you could say that, yeah. We're using the dimensions. We're just saying that there exists a 40-dimensional space, and we're placing tracks there. We could do it with 3 dimensions. We could say, okay, in literal space, we can have a track here, and a track over here, and a track way over there, and that one's way different than these. So, okay, I'm just parsing the input, basically, and decoding the crazy Spotify base 62. Don't get me started on that. URI. So this is basically it. You just say get nearest neighbors by item. You give it the track ID and the number of recommendations you want, or the number of items out of there. So and then I'm just basically looking up metadata. The actual lookup is a lot faster than what's going on here because I have to look up artist names and track names and everything. So that takes a little bit longer. So yeah, oops. Let's try it with 500. I think it's going to be dominated by, yeah, it's a little longer. It's going to be dominated by metadata lookups. If I do it again, it'll go a lot faster. It's all because of what's hot in the cache and what's not. So if I get this whole thing loaded into my laptop, it'll be faster. But let's take a look at that. So I mean, yeah, it's even 500 tracks down. There's stuff there that's somewhat reasonable.
How did you decide, you keep adding these latent variables?
Yeah.
You have to decide at some point how many is enough.
Yeah, so we just did some, right, we just did some experiments.
Just like looking at it and saying, oh, this looks...
Oh yeah, so the big question is, how do you quantitatively evaluate how good this is? One of the ways we do that is with radio feedback. Every time you play a track on a radio and you use thumbs down, that's a signal to us that those tracks may not be the same. It's a pretty noisy, weak signal though, because you might thumb down a track for all kinds of reasons. So, that's one of our sources of feedback. It's something we kind of struggle with. We have, people manually annotate, these are similar, these are not, but we don't have a huge corpus that really tells us how well we're doing.
If you thumb a track down, does it ever show up again, or do you give people a chance to thumb it down more than once?
It's not supposed to show up again. There may be
It
bugs.
signal a lot stronger if people continually
Yeah.
put a thumbs down.
Was there a question over here?
Yeah, you mentioned before how you care about the end songs, the songs that you listen to all the way. How do you deal with free users if they run out of skips and they're forced to listen?
We have a lot of filtering on what comes out of end song. I can't honestly say that we thought of that. Maybe we should. We get a lot of context information, like how I said that end song is 500 gigs a day of logs, and we really pare that down. But there's a lot of information in there that we can use to filter. Like, Well, yeah, if you played the track for less than 30 seconds, we don't count it, and if you skipped it and whatever. I don't honestly know. All right. Any other questions? Yeah.
Real meta question now, but have you ever filtered this operation by geographic location to find that UK users consider different sets of songs similar to Australian users?
I think you've asked me that before. Somebody did. Somebody did last time. Yeah. So we acquired a company called Echo Nest in Boston, and there's a guy there, Glenn, who basically does stuff like that all day. He comes up with all kinds of cool stuff. He actually defines genres. Like he comes up with, oh man, I don't even know. It's like death mathcore. He'll find like whatever that is. But yeah, I don't know off the top of my head. You'd have to ask him. But certainly, it's definitely different among different populations. Yeah.
So we've talked mostly about measuring the similarity between the tracks. Do you do something similar to measure the similarity between users?
Yeah. We've had a couple projects like that haven't really taken off. Spotify does have a feature that tells you, because we have a sort of social network, you can follow people on Spotify. It does show people who to follow. But honestly, I have not looked into that project in a while. So I know somebody was working on that. And, this seems a natural thing to do. But I don't honestly know whether who to follow is using that or not.
So you don't know if you're seeding that with the social network or not, or if you're...
It's mostly through the social, like that who to follow thing right now, I think mostly works through triangle completion kind of stuff in social networks. These two people are whatever.
Is the who to follow recommendations driven by the... Oh,
Yeah, it might be now. It wasn't last time I looked at it. Somebody was working on it. I don't honestly know.
I forget, does Spotify have like a dial for when you're doing the radio, how much variety you want?
No.
I don't remember.
Yeah, there was a startup that had something like that, and it might still. We could do something like that.
I was just wondering how you would do that, because like you can't really go on a list here, because that's
Yeah.
that's not very far away from the
Right. And I can think of some ways to do it with this latent factor space, because you could say, okay, I'm willing to go this far away from this track, and if you start adding more, then we can kind of define like a subspace in there and say, okay, tracks around here look good, and also tracks around here. But right now, radio doesn't work that way. It's not based on any kind of, it uses machine learning, but it's not a machine learning algorithm that tries to learn what the user wants. Radio is always in flux. There's a lot of stuff going on in radio right now. Okay, what was I going to do here? I don't remember. I think we were done with this demo, right? Okay. So, because we have this nice fast index, we could say that whenever a user hits the service, we can just give them their recommendations off of the index. But we actually do it in Hadoop because we can do a lot of other processing and batch processing, and it just helps. So we do it all in parallel. Once again, we use the distributed cache idea. So that 1.2 gig index just goes out to the distributed cache. It's not a lot for Hadoop to handle that. And so every little mapper. So this is one machine. I don't know what DC stands for. Honestly, I forgot. But these are all on the same machine, and they're getting the same. Distributed cache. They have the same distributed cache. So it's kind of it's pretty efficient. It's a lot faster than like having MapReduce clone out the data. You could envision another way to do this, which would be to. Well, yeah, it wouldn't work very well, so never mind. But we use we use the distributed cache to propagate the Annoy trees, and then so it's mmap. So all of the mappers on the same machine are using the same memory. It loads up into cache pretty fast, and then it's super fast to run through the data. And then I think I have a reducer here. It's actually done in the reducer, not the mapper, but it doesn't really matter. So we load up the user's vector, we load up a bunch of stats like which artists they've listened to, and we can kind of correlate back. I'll talk about because we also need reasons for recommendations, which I'll talk about in a bit. oops, sorry. So that's how it works. So related artists is another application of this whole thing. This is the related artist page for, well, you can't even see it on there. But yeah, it shows a bunch of artists that users who listen to this artist also listen to this, same as Amazon. So it's great for just browsing around Spotify, doing some discovery of new stuff. But the other thing is when we generate recommendations out of this machine learning model, if it presents something to you that you've never heard before, you don't know what it is. So you're like, well, why would I listen to that? So we need to come up with a way to tie it back to what you're familiar with. So what we actually do is keep a tally of how many times you've listened to every artist. And for the artists that you've listened to the most, we say, okay, well, if anything's related to these that's in their recommendations, we'll group them up and say, okay, well, these two artists that you've listened to are also similar to these things. So that way I know when I see this, it's like, oh, okay, that's going to be like some kind of instrumental progressive metal or something like that. So, yeah, that's how that works.
So you kind of rely on the user knowing what those other
Yeah, because
are.
we've
You're
seen
not
that.
saying because you like fast music or whatever the case may be, you're not putting it
Yeah,
together with that rationale.
we've experimented with that because we have a whole list of genres that. So just as the same with artists, we keep a tally of how many times you've listened to like various subgenres and stuff. So this will sometimes say, I forgot what the exact wording is, but yeah, it'll name a genre there, and it'll not just be anything from that genre. It'll be stuff that's recommended for you in that genre. So yeah, any artists that are named here, you've listened to at least a bunch. The problem is when you start using Discover a lot, you start just kind of clicking through and listening to an artist a lot, and you don't know what it is. So it can be a little bit confusing, but it works pretty well.
On that note, is there a user out there that you can use this to essentially buy copies around y'all?
Yeah, one of our VPs plays bedtime music for his kids every night, and yeah, it kind of latches onto that sometimes. So you've got so even though you've got a single space and you're saying that these two tracks are in like near each other, when you're in 40 dimensions, it's really hard to visualize what's going on. But you can be near a lot of stuff in 40 dimensions, even if you're pretty far away. But it does fail when people do. Yeah, I mean.
This is why Netflix has different users. Advocates you provide for a comment.
Yeah, exactly. Yeah, so sometimes, yeah, that happens. Like if you play bedtime music, sometimes it latches onto that. And then when we retrain the next week or something, then it'll just flip over to something else. We do a certain amount of filtering when we train too, because there are users who listen. There's like a user that listens to one song over and over like 50,000 times. And that doesn't really, there's nothing we can learn from that.
Crazy.
Yeah, I think it's like a store that has something on a loop or something. I don't know. What's that? Yeah, right. And we know exactly what you're going to listen to. It's pretty easy to predict. And there are some where people listen to, like this one user listens to 10 million tracks, and it's just too much. But so during training that's a problem, but actually during aggregation and recommendations that's not a problem. We'll be able to do the math. We'll be able to present something to them, but yeah, it may be WTF. So it happens. I know it's something we tweak stuff and try to like one of the things we've tweaked is that confidence fudge factor thing. Like instead of making it linear, we actually make it logarithmic. It used to be alpha times the number of plays, but if you played something 50,000 times, that's huge. So we instead scale it by the log instead, and stuff like that. Like tweaks like that help a little bit. Yeah. No. And yeah, that is a bias because it could be a record that a user would play a lot if it hadn't been released yesterday. So we don't have any kind of time-based normalization. That's an interesting idea, though. Yeah.
Any relative ties?
What do you mean?
So you're talking about like your VP playing bedtime stuff,
Mm.
and then maybe death metal during the workday,
Right.
in the morning like yoga.
Yeah, that's probably exactly what he plays. He's Swedish, so everything's death metal. We don't, we could do that, but it's hard to come up with like the segmentation. I guess you could do it by hour. You could have like a different, yeah. Like the programming, like when you load the browse page in Spotify, it actually is programmed by hour. There's a team of content editors that do that. So yeah, we could learn from that. We don't do that now, but we probably should. All right, anybody else? Sorry? Yes, that's true. That's true. So, because we're using dot products when we recommend items, the magnitudes of these vectors actually kind of change things. So, which allows the model to predict that popular items are played a lot, which is great. So you're likely whatever the most popular song is, you're likely to have played it no matter who you are. So the magnitude of that vector song is actually big. But when we want to find things that are similar, that's not that helpful because everything that's popular is similar to everything. So we use cosine distance instead, which is it's the same thing as the dot product, but we're just dividing by the magnitudes of those vectors. And here's just some examples of similarity. Tupac is, of course, 1.0 similarity to Tupac, and then 0.91 to Notorious B.I.G., Dr. Dre, etc. So I mean, those similarity numbers make sense. -1 is actually the worst score you can get. 1 is the best score. And so what it's measuring is the angle between these vectors rather than, or the cosine of the angle between the vectors, rather than the.
I'm sorry, would you ever get a -1?
Yeah, if you have a vector that's this way, you can have this space is actually positive and negative.
Sure, but like Tupac to Tupac is 1.0, so that's completely. I look at it as like correlation, so it's like perfect correlation. So who's
Who's exactly opposed to it?
like,
Okay, you're right. There isn't a lot of stuff that, like way over here. There's
maybe Vivaldi.
but actually Vivaldi's like over here. There's if you look over there, I've done it before, and you just get the weirdest stuff, like the train sounds and like cell phone fart noises, and it's so weird. And actually you also get like Chinese stuff and stuff in completely different languages that just doesn't map. What's that? Sorry? Dark matter, yes. We should investigate that phenomenon, yes.
So, does this, so one of the ways that you can break or you should be able to break the Amazon recommender system was to publish your own book and then rate your own book and then all of the top favorite books.
Yeah.
So if I published my own song, like Fart Noises or something like that, and then I created a user account, listens to that a bunch, and then listens to Tupac a bunch.
Right.
Create false positives.
Let's see. Yeah, you could. That's called a Sybil attack. If you created it'd be very expensive. I guess we still do it on free users, so you could still do it. You could probably bias things a little bit, but if you're doing it against Tupac, you're up against millions and millions of people. So, and the way we weight.
We created an extremely similar track because your user account, the only two songs that it's listened to has been those two.
I guess that's true. It would put I see what you're saying. So the only weight on that vector for that thing that you uploaded is going to put it there. Yeah, that's true. That's a good point.
It's based on your user, I don't know.
Yeah.
It's based on that one user account. Or if you could create multiple user accounts.
Yeah.
It would make that sound very similar to one.
That's true.
It would be very similar from your point of view, but it would only be 160 million.
Yeah, but
Everybody else stuff.
But it doesn't really matter because, the other thing is the vector magnitudes do come into play here. But yeah, you're right. Because we're using cosine distance, it might actually, if you put the vector like right there, it actually would be similar. Yeah, that's true. That could be an attack. Most attacks right now, like spamming, is done based on search term similarity, though. So they'll just upload a Kanye West album, and it's basically there's like a cottage industry of people who do like remakes of songs and call it exactly the same thing. And it's actually there is a kind of a separate anti-spam effort that happens here, but it hasn't been a huge problem yet. But I imagine that in the future it will be. All right, so. The goal of the spamming is to make money because every play you get, the artist makes some money. So it's, yeah.
So have you definitively proven that that's actually like Kanye West is uploading?
No, not like somebody's uploading like, you know, exactly the same song title.
Sure.
And it's like a remake. It usually happens when it's, you know, like if right now, Shake It Off, you know, got uploaded. And it was something like Taylor SW1FT or something like that, you know, that would show up in the search, and then people would play it because the original one's not there. Yeah, this was a problem. Like Beatles tribute albums, for instance, were really ranked up there, and they really shouldn't have been, but because we didn't have the Beatles. Yeah.
Well, I was just gonna say, I've seen a ton of those
Yeah.
fake tracks.
I'm sure.
And how hard is it to divide it? How hard is it to do that? Like, not that I'm gonna do it, but
How hard is it to make a fake track and upload it?
Well, how hard is it to upload something to Spotify?
Right now, kind of hard because you need to have some proxy record label or something. I've never done it, but there are some employees that actually are in bands and upload stuff. I actually don't know, but I think we're trying to make it easier, which means, yeah, we have to step up our anti-spam game. All right, so related artists. Yeah, that's what we were talking about 30 minutes ago. Okay, similar to user recommendations. So we're doing pretty much the same thing. We actually use a lot more models for this. The reason we only use one model for Discover actually is because it's so easy to compute that one and easy to roll it up every day and keep it up to date. But we have a lot more machine learning behind everything. So we've got the implicit matrix factorization that I've been talking about. We've also got an algorithm which is similar, but it's more probabilistic in nature. It's kind of similar to logistic regression over 4 million items. We use Google Word to Vec on playlists, where we treat each song as if they were a word, and then you know, like the sequence of words becomes, you know, causes an association between these things. Word to Vec also produces vectors, just like everything else, and you can use it, treat it in the same kind of latent space. And then we acquired last year a company called Echo Nest, who I'm currently working with, and what they do is they provided radio to like RDO and a bunch of other streaming services. And one of the ways they do that is by scraping the web and seeing, you know, if there's an article about two different artists and saying, okay, these guys are totally, you know, the same, then that creates an association, and then they can find cultural similarity based on what people are writing about these artists. They do, you know, sentiment analysis and things like that. So, related artists, we query approximate nearest neighbors, and we generate a bunch of candidate similar artists. And then we use all the models to take those candidates and rescore them. We combine them and we rank them. And we rank them based on an ensemble of models where we take all these models and we need to figure out, you know, how strong of a weight to put on the score of each one of those things. And that's where we use, well, I was saying before, the radio feedback, like thumbs up, thumbs down from radio, and skips from radio. That kind of gives us a little bit of feedback on whether artists are similar or not. And so we kind of use that to calibrate how much we trust the similarity coming out of each of these models. So we do that, and we just pre-build a table of 20 nearest artists, and that's what you show on the page. Radio. So same thing as related artists. We're just doing item-item similarity. Same thing, we generate candidates with the various approximate nearest neighbors, score them all, rank them, and then we store 250 tracks into Cassandra, which is where we store our radio index. So whenever a user hits play on radio, it loads up the index for that particular track out of radio, and that will populate a list of 250 tracks in kind of a virtual playlist and shuffle that. And those tracks have like weights on them based on how similar they were originally. So if you thumb up, whatever song you thumbed up, it actually loads in more tracks from whatever that was. Thumb down, it's supposed to basically remove that song from the list, but it downweights it a lot. It doesn't actually remove it. So, and there have been bugs where you'll just get the same track over and over, and no matter how many times you download it. In fact, that can happen if, for whatever reason, it only found one similar track. So yeah, we remove the song and try to reweight things. And then, so yeah, that's it for the main thrust of this talk. I didn't really have time to prepare slides because it's already 7:15. But I also want to talk about some other things maybe in the future. Oh, are we? All right, we're back. So last summer we had an intern named Sander Dieleman come over from Ghent University in Belgium, and he won a couple of Kaggle competitions on deep learning. He's super good at it. So what he did, there's a great blog post here. I will post some comments on the Madison Big Data site so you guys can see these links. But he created what's called a convolutional neural network, and what it will do is it'll take this. This is an audio spectrogram. So this is a song. These are the different frequency bands of the song, and the color indicates how much power is in that spectrum.
And it's time.
So this is time.
Okay.
This is frequency. And so what it is it's a neural network that it's a convolutional neural network, which means it's like it kind of takes a little window. They're called filters. So it takes a little window and just slides it over the track, and that I don't know how to best to explain it, but that filter kind of produces one item in here, and then so as it slides over, this filter is it's producing like a certain amount of output, 0, 1, -1, whatever, and then that goes into the next layer, and then there's another convolutional layer that kind of goes over that again. Again and again and again. There's a bunch of convolutional layers. And then, so what he's doing here is this 40-dimensional vector is one of our latent factor models. He's using this using the song to predict where it would fall in the latent factor space. And the reason we're doing it this way is because when you learn, when you use deep learning, you need to have some kind of objective. The goal of this is for us to say that these two tracks sound the same. And there's another regime of doing convolutional neural networks, which is called an autoencoder, where you take a track and you try to reduce it down to a small dimension and then try to reconstruct that track again. And that's sort of, that method can kind of work, but the representation you get might not be what you're looking for. It might be like, oh, these particular MPEG artifacts are, in this track, and these two tracks use the same encoder or something. It's not like they sounded the same to you, they sounded the same to this computer. So by using this objective, which is what people are saying is similar, we can have the network learn what sounds the same. So we train all of this. We learn this crazy huge mapping that gets us back to our original vectors. And then we can just throw all this away and say, this is our nice representation of how similar tracks are. We don't really care how well it predicts latent factor models. We just want to know what's similar or not. So this is a really cool project, and I am on the team that's currently computing, on 50 million different tracks, these convolutional things. So it's going to take us a while. We only have a pool of 10 machines working on it right now, but we'll get it on all tracks, and we will start using the similarity model. And so that will be purely based on what it sounds like. So when we get a new track uploaded, we can kind of put it with other things that sound the same.
Is that for spam detection?
Yeah, we can. In fact, with regard to spam detection, the other thing I'm working on right now is content deduplication. So we acquired a company, as I said last year, called the Echo Nest, and the other thing that they do is audio processing. They find all the beats in the song, and they find so they know the tempo. They find the chords. They don't actually produce a transcription or anything, but they know the basic tonality and the key. So they do a bunch of cool stuff like that. But the other thing to do is fingerprint songs, so that if you take a song and totally permute it, but it sounds kind of the same, we can say, oh, that's the same song as that. So what it does is it looks over the spectrogram and just kind of picks pieces out of it and says, okay, this is one of 1,000 different things I've seen before, very similar to. And so we look at sequences of those aligned in time, and every song, like a regular 3-minute song, produces about 1,500 of these codes per track. So the challenge then is saying, okay, well, I've got 50 million tracks here. I've got a new track I've uploaded. Here's 1,500 different codes. Now, which 1,500 codes do those map to? And do it on everything. So So if you're doing one track at a time, that's not too bad. But if you need to like start from scratch and cluster everything, that's kind of hard. That's what I'm working on. There's a technique called min hashing, which is kind of mind blowing how it works. I don't think I really have time to talk about it, but it turns out that you can take just like 100 of these, if you've permuted them in a certain way, and just compare those, and the probability that you have a collision is exactly the same as the what's called the Jacquard similarity between two sets. Kind of hard to explain. I don't have a slide for it, but it's neat. And then there's another algorithm called hash2min, which has nothing to do with this, but it lets you find the connected components super fast. So if we know that these two tracks are the same and these two tracks are the same, and we've got 50 million of those, we can find all the clusters in 5 MapReduce steps, and each one takes like 3 minutes. So super cool stuff. But yeah, that's all I've got. So thanks for coming. I hope you enjoyed. Any more questions? Yeah.
I'm just wondering if you look at regional
Yeah.
comparisons. I mean, people, let's say bands that play in a particular region. I'm thinking of Seattle and Nirvana, or Cheap Trick and Rockford, or something like that. And whether or not people would be interested in those bands, that type of genre.
Yeah, I mean, that sort of thing should be kind of reflected in the model already, but it's hard to say. You can look for that kind of thing and probably find it if you look hard enough. We don't explicitly model where the band was from, though we do have bioinformation like that.
But if you, that's why I was wondering about if you have your social network tied in there, because if you're, a lot of the times you like the same music as your friends, so if your friends' recommendations were more strongly weighted than Joe Schmo's recommendation, that might catch that.
Yeah. I think we've played with weighting based on social network. It's kind of hard to implement, honestly. But we, at least for me, that's not that true. None of my friends really listen to what I listen to, except for my music friends on Spotify, which, yeah, I mean, you can make the case. Usually how that works is you just follow people on Spotify, and whatever playlists they make show up in your feed. So it kind of emerges naturally into the latent factor model that way. Yeah.
For the neural network learning project,
Sure.
I thought you said your 40 factors changed every time you ran that algorithm. Are they similar enough that you can just take one representative set of them and the average over many times? That's the kind of forms of basis state.
Right. Yeah. So we just took, we trained the model once. Use that as training data for, so after having trained that model, we have to go back and get the audio and map the 4-dimensional vector to each audio track. So we kind of do that once and train this neural network. But as I said, once the representation has been learned, if you do that again with a new 40-dimensional vector, it's probably not going to be a lot different. Yeah. So we just throw away the top layers and just take the representation, the dense representation of that track. Yeah.
When a new song is released or an album uploaded, do you assign a random vector based on its genre, or how does a new song get incorporated?
Yeah. New songs, basically, we don't have any allowance in the algorithm for finding new songs. So what happens is, every time we retrain, everything's random initially, and then but for new songs, the way that new songs get in the system is that we use the related artist feature and say, okay, here's a new album by somebody that you've listened to a lot, or by somebody related to someone you've listened to a lot. So by alerting people to new albums separately from this system, they get kind of initialized. So we don't have a way in there right now. I mean, we could, though. We could say, here's a new track by Nirvana. Well, of course, there wouldn't be one, but we could say, we could put it in the centroid of all of Nirvana's tracks or whatever.
So is there been any kind of insight as to, so I'm guessing after a while, these ID vectors kind of more or less stabilize. I mean, you're updating them every week, but I'm sure they don't move that much.
Relative to each other, right.
Huh?
They don't move relative to one another.
Okay, yeah,
But
has there been any kind of investigation over time, like every week, are you saving any of this data?
we do save. I mean, we have models going back at least a year weekly. So we could investigate this sort of phenomenon. I am not aware of any effort to like basically take a bunch of representative artists and plot their similarity over time, but that's a great idea. We have not done that though. Yeah.
You said only a year. What did you use before this?
Well, we've used this model for a while, but we've had a few HDFS mishaps. Let's put it that way. So, and it's not, they're not really. Nobody's really thought of them as valuable data to keep around. So it's pretty much they just expire after a while.
You have to call it data aging strategy.
Yeah, exactly. So Spotify has another tool called Snakebite, which is a Python reimplementation of the HDFS client API. And the reason that we did that is because when you type Hadoop FS LS or whatever, it's loading up Java in like 300 megabytes of junk, all the jars and stuff. When you type Snakebite LS, it's loading 100K of Python and just connecting to the server. So it's fast. Hadoop's security mechanism is kind of the honor system. You basically say, oh yeah, I'm root, and I want to delete this. And it's like, okay. So when you implement your own client, you have to be careful to implement security on the client. So one of our engineers was just like, he typoed something, and it just removed all of /discovery, and instead of moving it to the trash, it actually deleted it, which... So yeah, there was an emergency patch to fix all that, but yeah. Luckily, it's like /discovery is something that we can just, in Luigi, we can be like, okay, build today's model, and it'll just find all the dependencies and just go work for 2 weeks and just rebuild everything. So it's nice. Yeah.
I was going to say, maybe that's what the 300 megs of Java code was doing.
Yes, it's very safe. Yeah.
Do you relate commercials to songs or artists?
We didn't before, and I don't know whether we are now, but that is something that is definitely being worked on. Because, yeah, it would be like, you could be listening to death metal, and then, right, you'd get, this is Blake Sheldon. It would be very incongruous. That would happen all the time. And I think that's a little bit better now, but I don't know how it's implemented. It may not be with this, but it may be with, some other Echo-Nest genre system or something like that. I don't know. Spotify has grown so much in the last 2 years since I started there. So, I used to know everybody who's working on all this stuff, but it's tremendous how much we've grown. So, yeah.
Have you ever looked to see which tracks are most closely clustered with each of your factors in your 40-element model, like the unit vector tracks of your model, and see what kind of, does anything interesting stick out when you do that?
I didn't quite follow.
I mean, so you have this model, right? And you've got, there's a similarity to the 640 elements. Are there certain songs that are the most similar to each one of those elements?
Oh yeah.
That's how you sort of the genres.
Yeah.
Represent, or...
The thing is, so that space is not necessarily aligned to any particular axis.
Yeah.
So what you could do is compute an SVD or something like that.
Yeah, take the eigenvectors.
Right, the eigenvectors of that big space. I've done that before, but yeah, honestly, I don't know why, but I don't get anything that looks like, oh yeah, this is definitely, this is obviously, on a different, this is obviously orthogonal to that. Yeah, not really. I mean, you get the rap country dimension, that kind of falls out. But there's not a lot else that I can think of. I'm sure, if I put it up there, somebody would find a pattern, but yeah, it's fun to play with this stuff. It's kind of an occupational hazard because it's so much fun to just mess around and listen to music all day. So, yeah.
Back on the question that was asked back here about a new artist. So, okay, new track comes in. Obviously, if it's a track by an artist that already exists, it's pretty easy to find that track.
Yeah.
If it's a new artist and a new track,
yeah,
you
that's.
kind of drop it in and see where it falls.
Yeah, that's the hard part. There's a lot of promotion that happens. So let's see. I think so in a lot of cases, for instance, we didn't have Pink Floyd, and then we had Pink Floyd. There was no relation from Pink Floyd to anything else, so we went in and manually added some of these associations so that would, it was a big launch. But if you're not Pink Floyd, it's not quite that easy. There's a couple artists that have launched on Spotify that way, where we've promoted the hell out of them, and then okay, now they're in there. But otherwise, it's going to have to be word of mouth. There's no. So yeah, I mean, hopefully when we implement this, hopefully we can do something decent with that. And in fact, when we were playing with this, just because a song sounds the same, you might get something super popular and then something super obscure. Maybe you want that, maybe you don't. But when I was playing with this, it actually was relatively coherent. Like I would put in music that I would expect, based on popularity, whatever. I get something that was actually pretty genre coherent. It wasn't like throwing in, Chinese music or something like that. It was, I don't know why. It works better than it should, honestly. Yeah.
Because of the window that you're using in it, do you find it picks up some kinds of similarity better than others, like tones versus beats versus
Yeah.
song structure?
Right. Sander has a great blog post that kind of goes into all the stuff that it finds. It like these filters kind of pick up on certain different things. Like one of the filters was like tremolo or vibrato singing or something like that, and like very harmonious a cappella versus heavy guitar or something like that. So yeah, there's interesting stuff that comes out of that. Yeah.
What do you see the future of the recommendation engine? Is it more of this? Is it a combination of both of those?
Yeah, there's So yeah, we definitely want to combine this in there. Lately, so the guys on that team, so I've moved teams. I'm now doing audio fingerprinting and stuff. But the guys on that team right now are optimizing their pipeline because as our Hadoop cluster gets bigger, it gets more and more used. It's kind of odd how that happens, but it's very, very busy. So they've been working on just doing engineering tricks to optimize this stuff. So that's kind of the big effort now. But there's always different experiments going on, different models to add to the ensemble and stuff. But as far as like big, impactful things, I think this is probably the first step. And also Echo Nest's work of cultural similarity, scraping the web. We can do more work to combine these things. Yeah.
Do you use the actions taken on the recommendation page for validation?
Sorry? Oh, yeah. So when you're looking at your Discover feed and you play something that's been recommended to you, do we use that as feedback to ourselves? Is what you're asking, right? Yeah, we don't.
More than negative, where someone clicks it doesn't make it.
We don't do that either. So we filter that stuff out. So if you're playing a recommendation off the Discover page, it does feedback. It does count on your play count, but it's actually like 0.1 or 0.01 plays. There's a bunch of ad hoc context weights there, which we could probably play with some more. So yeah, that's a big problem. And in fact, the other problem with using radio feedback is that we have a lot of feedback from radio, like thumbs up, thumbs down, skip, everything. We have feedback on pairs of songs that we've recommended before, but we have absolutely no feedback on things we haven't recommended before. So as soon as you add a new algorithm in here, by all of our offline measures, it does great because it recommends something different. There's no negative feedback on it. So that's another huge problem. It's hard to kind of bootstrap that kind of thing. You kind of have to take that penalty and say, okay, well, we don't actually know how it's doing until we deploy it for a while, and then we can use that feedback. But yeah, we're definitely aware of the problem where feeding back into itself is an issue. But the idea where if you start playing a track and then stop it, we're not using it as negative feedback. Maybe we could. Yeah, you could. But just because you played it for a little while and stopped doesn't mean you don't like it, because you can preview tracks. But yeah, I think that's probably a good idea, though. Yeah.
Can you use A/B testing to feed different
Yeah.
algorithms to different?
Yeah. Not as much as we used to, but during the initial period when we were tweaking a lot of these models, especially for radio, we would release 8 or 10 different versions of radio, and we'd track the number of years listened to per day for all the different things. And if there was a statistically significant change, and there often was, we'd roll that experiment in. So yeah, we do a lot of that.
All right, cool.
Alrighty.
All right, thanks again, Andy.
All right. Thanks for coming back.
Also, 2 things. 1, grab pizza if you want. If you haven't eaten, if you want to take some home, be my guest. Also, Andy is consented to go have a drink on Cloudera over at the Silver Dollar, 1 round only. So if you guys want to come with us to go to the Silver Dollar, it's just right out there, you're more than welcome to. Thanks again.
Thanks.
All right, thought that worked out well.
Yeah.